thank you very much. Well, actually, the title is an overview, but an alternative title would be our own, let's say, pathway to getting educated in this classical, actually, problem, which is no more than the planetary periodic problem, let's say, with two planets in inclined orbits. Now, when I say we, I mean, apart from myself, Rita Mastroianni, this has been an important part in the end in the thesis of the project we presented in the next few months. So now, I say this because we started with sort of different goal in that project of Rita, which was to provide, again, in this famous Epsilon Andromeda system, heard about today, again, in the talk of Marcus and Soderberg. The main final goal was to get a KAM type theory for the innermost planet. Yes, closer to the microphone, of course. Okay, absolutely, no problem. So now, to do that, we thought of using an approach that has also been mentioned in another talk today, which was to use a kind of restricted model for the outer planets, so that you can have essentially a fixed time series for that orbit, so you can use for modeling then what happens for the inner planet. And then started the problems, because you heard about these two planets of the Epsilon Andromeda system. They have big masses. You can see a decade of masses of Jupiter. They are in a highly inclined mutual inclination of about 30 degrees. And there are models, and some of these models have been computed actually by the research group of Google nowadays and in the past. But since we have many uncertainties in the observations, we don't really know what is very accurate. And essentially, what we were finding is that there were several troubles in getting a good model. So you could change a little the initial conditions, and you could cause the arguments to behave differently. Rotate instead of librating, and so on. And when you were trying to put some order into that, starting, let's say, from the Laplace-Lagrange ability and moving on, you were discovering, for example, that because of a high inclination, you could lose the stability of one of the two normal modes. You couldn't say very well when this is happening. And well, these modes here you can see in the phase portrait, but actually Epsilon Andromeda is very close in this kind of structure that beginning looks like a separatrix, but then we'll see what it is. And another, so because of all of that, we just did what every person would think of doing at that point, which is going back to literature and see what is known about this type of systems. And then we discovered there is another huge methodological, let's say, zoo ideas that make it really, really very hard to put things in an order. For example, even in the way that you expand, I mean, either you choose to expand or to just do Caesar averaging in closed form after a multifold expansion instead of one basicity, for example. Okay. Put ourselves really into the difficulty of getting theoretical control over the problem. I think that was the main thing. And in order to do so, we realized that source of the problem was the lack of a clear separation of what part of the dynamics comes from the planar problem, which is secular problem driven, and which one comes from the space, say, degree of freedom. Because when you write a Hamiltonian, in particular when you do the Jacobi reduction, was mentioned before, in the classical, the textbook way, you don't see those two things separate. You don't see the space, and you just get the movement, and then you don't know what it is about. So we don't know how to write the good kept terminology that are there in Hamiltonian, if you have small masses out of which one is obviously executing the other one with inclination. Okay, so from that and first say, what do the people agree on? I mean, it was not just a disaster. So you start with the usual, this is the Poincaré version, the Hamiltonian, and you can easily demonstrate that the angular momentum remains an integral of the average problem. Easy exercise. See that. So it's not only an integral of the full, but also the average problem. And that implies that you reduce the number of degrees of freedom considerably. So you start with 6 degrees of freedom in heliocentric variables, 3 for each planet. And then with the conservation of the angular momentum, you have 2 components. You go, in theory, you go down to 4 degrees of freedom. You have to do with the Jacobi reduction to see that happen. Either you get it in the genesis that Philippe was speaking before. Now, in the planar case, everything is reduced, actually. So you can easily demonstrate that the planar problem is integrable. And so in the average problem, let's say in the space, you get 4 degrees of freedom, and out of the elimination of the freedom, and up to 2 degrees of freedom. So there is nothing that you're really. Now, about the Jacobi reduction, just to mention the small thing. So let's say you started with any secular model, say the seizures one, which is just average, fast degrees of freedom. The basic technique is very well known in the last 200 years, essentially. You need to essentially go to the Hamiltonian and recall that when you do averaging, essentially you distribute the mass in wires. So all that counts is the mutual inclination. Okay? So the potential depends only on the mutual inclination. Well, when you expand, you don't see that directly. You get a lot of sine I1, sine I2, and cosine I1, and cosine I2. But when you just substitute one of these expressions with the other one, then this mutual inclination, I mean, all these terms in the average model get eliminated completely, and you just get this difference. And then you also know that just because of that you are in the invariant plane, you have that the line of nodes is common for the 2 planets. Let's say they are in the antipodal points of that line of nodes, which means that they are arguing that the nodes are separated by pi. Always. Okay, so this is all standard stuff, and the Jacobi reduction essentially accounts on noting that if you just first do Hamilton's equation and substitute those invariances in the flow, or had you just substituted in the Hamiltonian and then reduce Hamilton's equations, the result, as far as the remaining degrees of freedom is concerned, has not changed. You lose one equation, which you can always recover by just getting back to the conservation of the angular. So, in summary, you can do it in the Hamiltonian instead of doing it in the equations of motion. That's all we do. Okay, so this is standard stuff. Let's see where it leads. If Irene probably can play the little video. Okay, so that brings us to a kind of, let's say, grosso modo evolution of these systems. Well, this is exaggerated both in scale and time, but what you can see here are the Keplerian ellipses, osculating ellipses of the 2 planets. And essentially, the information you can get precisely by the conservation of the angular momentum is that when the ellipses breed, this is a classical secular thing, then the oscillations in the eccentricity are coupled with the oscillations in the inclination. So the orbit reaches the maximum separation in the inclination has to become more circular. And when it comes closest to the plane, then it is the moment when it becomes mostly eccentric. So it's essentially this coupling with it. And of course, you have 2 limits, which will prove to be very important in what we discuss. The first one is when you have a purely planar case. In this case, there is no inclination. This breathing, through a normal mode of the Laplace-Lagrange theory, but without. The other limit is when you go to the maximum inclination case in which you can get circular orbits that have a fixed point there. I will call that second regime, I will call it the quasar, in the sense that you can have two planets that essentially are on circular orbits and do not move from that region. Remain there because that's a secular movement. Okay, so I think this is what we want to speak about altogether. Then start all the problems. I mean, so I told you just how people, to what the people agree methodologically. Now about what they don't agree. I mean, starting from the simplest probably idea, which is whether or not in the planar case, when you work with essentially Poincaré variable story, whether or not there is, what is the topology of the phase space? So the topology of the phase space, actually, we are used to create planes, but because of the conservation of the angular method, we want to speed. And that can create a lot of problems, in particular because in astronomical literature, the people tend to speak about these normal modes of the problem, like resonances, upside-down rotation resonances. But in the dynamical sense, resonance wouldn't just mean what an astronomer believes is let's say, a switch from libration to rotation, because this can be very easily seen that it's just a topological effect. So we have orbits which, by a slight change of initial condition, can be made to surround the origin or not surround the origin, secular plane of one of the two eccentricity vectors. And so you would see temporarily a difference between libration and rotation, but there has been no separatrix or unstable orbit or any bifurcation. So there is a problem even in the jargon. Then this is one of my beloved ones, starting from this very influential paper by Mikchenko and Malhotra, and then again, Mikchenko and Perras-Melot and Auger. Now, here you have an attempt to depict all basic possible behaviors in the phase space of the system. And I just invite you to, I have no time to explain what all those things are. These are contours of the secular Hamiltonian in a properly chosen plane. The circles correspond to lines of constant usually. Then you have in that same plot stars and domains called 1, 2, 3, 4, and discontinuities of any type you can imagine. Then you have red curves representing periodic orbits, which can be stable or unstable. There is a new thing. I would say there is an attempt to provide all the information, which in the end turns out to be, maybe for me at least, very difficult to follow by intuition. So, say the cost which you pay by accepting the fact that just by, let's say, the simple fact, which is the peculiarity of the system, that the topology of the phase space is the one of the sphere. So it forces you to introduce new variables and so on and so forth. Just by that, you lose nearly all of the intuition which we have when we just use eccentricity vectors, E cosine of the argument, E sine of the argument. This is the thing we use, this is the thing we understand. And so probably our difficulty in this problem was just stemming from this particularity. Well, here is another one. This is the group of Namur, the gears of Veneral, with Avan Sophie here in the audience. But this emphasizes, again, a different aspect of the problem. As we said, there are two limits. There is the planar limit, which all singularities and topological different. And then you have the cosine limit. So you want to understand, not in the restricted case, for which we know everything in the last 100 years, but in the case with two planets with comparable masses, and even non-hierarchical distances, and none of the approximations usually used, you want to characterize the transition when that, which is actually a function of the inclination, around 40 degrees, a value or so, when this configuration of two circular orbits that don't change in time becomes, from being just having a double stability, eventually one of the two modes becoming unstable. You would get that theory to characterize how the space looks like. And again, please check the use of different variables. Again, this is here you have another remark. This is related to the model. So had you decided to expand in eccentricity, you should be able to check whether your expansion is reliable in terms, for example, of the calibration of the error. But that's not what all the people do. So you have, instead, you could have chosen, as was said today, again, to do a semi-analytical, as the people use it, which is another name, rather say semi-numeric, which I believe is more correct in that case. Calculation of the circular control. And that essentially means that you use the trapezoidal rule or a Gauss integral to represent by a sum, say, all the fast period curves. And there are obvious advantages. We know, for example, the work of several people, including Giovanni Gronchi, here today, that this has at least one obvious benefit, which is the possibility to treat even this case where perturbation theory fails by definition, which is the case when the ellipses cross, so that you have a real singularity in the integrand function which you integrate, and you don't really know what to do with that. So we have theorems which tell you that somehow you can overcome this singularity, and on the basis of that, you construct models. And this is what the people do here. And again, you see in a different, again, set of variables, what you get, these are the contours of the secular Hamiltonian in the model, again, of that same type. And here you compare, for example, with the quadrupolar approximation, which would just distribute the mass in the wire and forget about the intersection point. So there you see the differences in the phase portraits, which are essentially reflected in this continuous part of the contours of the secular Hamiltonian change. Okay, so I think that was enough in demonstrating our own, as I said, difficulties in getting educated on that subject. Essentially, you have a jargon of different methods, tools, expansions, variables, and points of view. And you try to put some order into understanding the basic question, which, if I go a la Poincaré, wouldn't be different than just figuring out which are the basic, let's say, periodic orbits of the problem, or if you like, the basic low-dimensional invariant objects in a more general sense, whose bifurcation, chain probably of bifurcations would allow me to go continuously from one phase space structure and topology to another. Essentially, you want to understand the way that Poincaré would have suggested already 130 years ago. So now we'll tell you what we did, and I probably have a disclaimer on that there is maybe nothing new for you to learn out of what we do, because most of the thing is just methodological. So what we claim to do here is to put some order into all of that. Not that we discover some real new phenomenon. I'm not very sure about one only, I will tell you which one. But probably just a bit of research in literature will demonstrate that somebody has discovered that one too. Only that it would have been impossible to say just by the formulas. Okay, so what we did was, first of all, to get stuck in the logic that we have to get the problem from one of the two limits which we understand, which is either the planar or the causal. And since most extrasolar planetary systems have rather moderate values of eccentricities, looks quite more reasonable to start from the plane. So now what we want to do is to be able to write in some way the Hamiltonian like H planar plus H space. Be able to do a decomposition that makes sense. This stuff. And to do that, we return to Jacobi reduction. So what we did was this simple thing, which I used to call the bookkeeping. Is something we all do when we write a notebook for doing calculations, which is essentially to put a symbol that separates smallnesses. Something is of first order, something is of second order, so on and so on. Now, look how this is done. Is this symbol eta? There is another symbol epsilon, which means eccentricity. So probably angular momentum deficit. This is classical. Now, for the inclination, you get something in addition to that. And what you say here is that I will split the identity to two parts. So we'll say the cosine I is equal to cosine I minus 1 plus 1. Then the cosine I minus 1 is just I squared. And that's something which is, this is the essence behind, for example, modify the variables. So you do that and you return to the Hamiltonian, and actually there is a small technicality here, because if you have to do it with expansions in the eccentricities, you have to do that before you expand the denominators. Otherwise, you lose factors in the process. Now, if you work with multipole, there is no problem with this type, because anyway, the reason we work with multipoles is not to get any denominator of the one which you need to integrate in the form of the Laplace coefficient. So there, the problem does not exist. So you do this substitution and then expand your Hamiltonian in terms of this formal symbol whose value is equal to 1. Doesn't tell you anything other than separating terms. And when you do that, you really reach to have the separation you're speaking about. So that essentially you have a part where eta is not present, and that depends only on the relative argument. This is precisely the planar situation. And you get extra stuff, which depends on eta. And in that extra stuff, you may have there too some terms that depend only on the difference, which eventually, if you like, that a posteriori, the integral, let's say, part of the Hamiltonian. This is the magnet case. So you do that, and then you do not way more than the usual stuff. So you just go to Poincare variables and start playing with the Jacobi reduced Hamiltonian. And well, the first thing you can really see there is that by just doing this little trick of transferring all the omega 1 minus omega 2 terms to the integral group part of the Hamiltonian, you can extend essentially the Poisson, the Poisson structure of the variables of the sphere to be extended from the planar to the spatial problem. So eventually what you say here is these are the variables that essentially create a Poisson algebra whose angular momentum is the Cassini, so to speak. So essentially what you claim here is that in these variables, the reduction is done by 2 instead by 1. So it's just one of the equations which you lose in the reduction is just lost by the time 3 of the variables have, let's say, non-trivial commutators, while the last one has a commutator equal to 0. So then you do that, and you end up with a kind of Poisson system, which is another way to write the dynamics, the integral part of the dynamics. And then we do know that the surface of constant energy is just given by this cylindric surface, while the conservation of the angular momentum refers properly to the sphere where everybody let's say, lives. And so typically those two surfaces intersect on circles, which would mean invariant tori of the circular column, because you have one more extra frequency, which you don't see here. But on the tangency points, you get the periodic orbits themselves. And so you can do, and Rita has done a magnificent work discovering all these upside-down quotations, so to speaking. But here you see an example from the planar case, but you can do it also in the spatial case, so you can have this family of periodic orbits which essentially have aligned or anti-aligned pair centers. But the orbits would not necessarily be let's say, plane. The system would not necessarily be planar configuration. Now, you see again, you can distinguish, I have not much time to say about it, how all this sort of separatrix, which is not a separatrix, reflects on the sphere. And then you can even distinguish the differences in the structure of the Poincare section, which we're seeing here, and how to, you still get, in these variables, you still get one singularity. There is one pole of the sphere which transforms into a curve in the individual variables, but otherwise, most other troubles which you have in representation of stop. Okay. But so far for the integrable thing, there are more things which you can do about that. Because if you have a good representation of the starting point, you can start creating local normal forms around that. And these normal forms work well. Here you have an analytic, this is the work of the most recent ones of Rita Mastroianni, which you can see analytical versus numerical integrations of the periodic orbits, these ones, or even of invariant tori which surround them, one of which, in this case, for example, one of these tori just represents the situation we believe is the actual situation of the epsilon Andromeda system, the one that Mark was speaking about today. Okay, what about the cosine part? Well, this is a little sketch. I have two of those. Well, this is the restricted, let's say, free-body problem. And in the happy coincidence case, let's say hierarchical quadrupolar. And the happy coincidence essentially means that it turns out to be integrable, although there is no, let's say, basic symmetry that applies. So just a consequence product of D'Alembert rules. So you end up in the restricted free-body problem. You end up in the quadrupolar approximation with an integrable model that essentially shows that you have terms which are quadratic in this and depend on cosine of 2g. So let's say with the critical argument. So you just push those parts into the quadratic part and you diagonalize as it should. You discover that from a certain inclination on, the signature changes, and so the orbit turns to be unstable. And this is the classical, if we like, cosine-Lidov phenomenon. And this angle is about 39 degrees in the restricted free-body problem. And if both particles have mass, but the problem still remains somehow hierarchical, so you use the quadrupolar approximation, the particles much closer to the star, the other, then the angle doesn't play very much. So it's always around 39 degrees or so. And the phase portrait looks like that. But there is a difference. And the difference is that when you go in the full problem, your quadratic part of the component, say in Poincare variables, should always represent two modes. While in the restricted problem, one of the two planets is just in a fixed ellipse, and we don't care about it. So now you would expect in the phase portrait to see not just the transition to instability, but also the second mode, which somehow remains stable. So now we can start understanding. So this is a sequence of phase portraits, which we obtained essentially by working with this parameterization method. And we have, let's say, a transition from the upside-down connotations to the Kozai regime, which is actually in the real case is full of chaos. It's a stable mode, it's full of chaos around it. But you can distinguish here also the stable mode, the one that remains stable. Now, these are two different lines represent. One is a multi-pole expansion, the other one is a classical expansion, which is to demonstrate that the limits we have worked out, which are the appropriate limits, so that the two Hamiltonians essentially say. So we're pretty. And then you can distinguish that these are not actually so separate. So you can see the transition from one to the other is done by a kind of essentially subtle node bifurcation, which you can see here. So we try to understand this plot. This is the last thing I want to show you today. Well, here you see again the quasi-periodic orbits around the excited rotations fit by a normal form. Okay, here you see this transition better. So we name the upside-down rotations A and B. And as you can see, you have a subtle node bifurcation. And these orbits, called C2 here, you have C1 and C2. And C1 is unstable at the beginning, but very quickly becomes a stable periodic orbit here, which grows in size, while the mode called C2 goes eventually to the unstable orbit of the cosine mechanism. So essentially what we claim is the chain. This is the result of, we don't know how much we could claim it is new or not. That this orbit here, which comes out of this subtle node bifurcation, essentially ends up being the stable mode of the maximum inclination regime, while the other one, which started its career as a stable periodic orbit, eventually gets stabilized and ends up as the unstable orbit of the cosine mechanism. And here just I finish with a little sketch, because these are essentially predictions written on paper, and then we have to see if that works out in practice. You all know very well what I mean about. I got the conclusions. So theoretically, whenever you have a Hamiltonian with a non-trivial phase-space topology, you need to change your variables, and it's always an interesting exercise to provide new sets of variables and new points, standpoints, even in the algebraic treatment or of any other dynamical system. But from the point of view of insight, we eventually figured out that with all their deficiencies and need of splitting the phase space into and examining probably limiting cases of prograde, retrograde, and so on, when you are in the planetary problem, parameters are not extremely bad. These are probably the usual, essentially Cartesian variables in phase space, harmonic oscillator variables, are still the best to use from the point of view of insight. And another thing is that if you want to really get the composition that allows you to start doing some theory, we found it useful to introduce a bookkeeping scheme already at the level of the Jacobian class. Then we have a way of understanding the transition in terms of periodic orbits from the upside-down rotations to the Kozai regime. And all these features are nearly suppressed and inexistent when you treat the hierarchical case. The mass ratio is very different, the distance ratio is very different. So you need to work with intermediate values of the same major axis and the mass ratios to be able to distinguish effects. But this is what reality speaks about. Most solar planetary systems really need like that. Now, with spin mass, that was a question asked also by Hugo several months ago. We are in progress of developing a perturbative method to eliminate legally killing with the canonical transformation to solve for your terms, so that you can get a better model of order 2 in the masses. And such a model would actually be able to treat also the mean motion resonance machine. Well, these are all the problems I think. Stop here, so thank you.